Now in the previous example, our base is in the XY region, but our slices were perpendicular to the x-axis. In this example, our cross sections will be perpendicular to the y-axis, so that means that we will need to use the y value, the y-axis as our integration domain, and then we need to rewrite the function in terms of x. So in other words, we have to solve for x, and if you solve for x, you have to raise both sides to the 1/3, therefore you get y to the 1/3. So that's the first thing we have to do. Okay, but before we do that, we need to use the original information to sketch the given information. So it says that the graph is bounded by y equals to x cubed, which is a cubic function, and a cubic function is going to look like this. So the graph's going to look like this, like that, and then that's a cubic function, right? That's a cubic function, and then the function y equals to 0, so this is y equals to 0, and then x equals to 1, so there's x equals to 1 somewhere here, so there's x equals to 1. This is the region we're interested in. So we sketch the region, and it says that find the volume of the solid for each of the following cross section taking perpendicular to the y-axis. Okay, perpendicular to the y-axis. So first of all, let's identify these two curves. This is the curve x equals to 1. This is the curve x equals to y to the 1/3. And the reason why we need to solve for x is because we're taking the cross sections perpendicular to the y-axis. This is the y-axis. This is the x-axis. So these are our cross sections. They are no longer perpendicular to the x-axis, but they're perpendicular to the y-axis. So they look like these guys. They look like that. Okay. All right. Now we need to identify this bound, this upper bound, and this lower bound so that we can integrate. And as you can see, when you plug x equals to 1 in here, you get y also equals to 1. So this is also from 0 to 1. Now we want to know what would be the volume of this solid if the solid is formed using equilateral triangles. So then you have equilateral triangles popping out, just like how we did before, right? So we begin by identifying the area. So area of equilateral triangles, all right? So remember that the area function in this case is going to be in terms of y, root 3 over 4. We're still using s squared, okay? So s is going to be this length right here. That's s. This is s. Now to find the length of one of these slices, you basically take, in this case, you take the right function minus the left function. And the right function, so s is equal to right minus left. Okay, so the right function is the function 1. That's the right function. The left function is the function y to the 1/3. So that would be s. So once we have found s, then we can set up a definite integral to find the volume. So a is going to go in there. And by the way, before I write that down, I should have written what the area function is. So area is root 3 over 4, and then I have to replace that in for s, and then I have to square it, and that's what s is. So that goes in here, and then I integrate that with respect to dy using a calculator to finish my job. I can always store that under y1 if that makes it a bit easier on you. 1 minus x squared, x to the 1 over 3, square that, leave the screen, math 9, 0 to 1, and that's y1 dx, and you're done. See? Enter. I think and it's doing the calculation, 0.043. So this is 0.043. Okay, very good. Let's do part B. Okay. Squares. So area function when cross section is a square. Okay, good. So remember, a square, these are squares, so they pop out of the screen. Okay, so they look like these. They're squares, right? They're squares, they pop out of the screen and they go. So you got a whole bunch of these. Area of a square is, remember the area of a square is s squared. We know what s is. We plug that in there. 1 minus y to the 1/3 is s. Square that. That gives you the area function for a cross section. And then you find the volume by setting up your integration from 0 to 1 of the area function. Okay, so let's see what we get. Math 9, 0 to 1. And the area function is that. So we can basically type that in here. 1 minus y raised to the 1/3 we got to square that, close parentheses, square that, dx, and we get a lot of work, as you can see, 0.099. So 0.099, that makes it 0.1. Okay. Part C, rectangles of height 2. So rectangles, so area function for a rectangle of height 2. Okay, so the area function is, so remember, this is the length of the rectangle. Now this is the height of the rectangle, but we know what the height is. The height has a length, the height has a value of 2. So then it's really s times 2. That's how you find the area of a rectangle. We know what s is. Again, this is s. So replace that with y to the 1/3 times 2. And the volume just comes along. So volume is going to be from 0 to 1. The area function, there you go. And let's type it into the calculator. And hopefully that's easy enough, guys. Math 9 from 0 to 1. Okay. We have 2 times 1 minus y raised to the 1/3 dx. That gives us a value of 0.5. So that's the volume for solid that's formed by rectangles with a height of 2. Okay, D semicircle. So area, so volume, if cross sections are semicircle. I'm a little bit more descriptive here. So the first thing we have to do is we have to find the area of a semicircle. Okay, so that refers to the area function from the previous page. The area of a semicircle is 1/2 pi r squared. What is r, right? So r is just half of whatever s is. That's what r is, because technically this is a semicircle, right? You get a lot of semicircles. Remember, these are popping out of the paper. Okay, so they're popping out of the paper. So we know what s is. Divide that in half. You get the length of the radius. That's what's needed to find the area of a semicircle. So from part A, we know that s is 1 minus y to the 1/3. In part D, we take that, we split that in half. That's the radius. And then we set up an integration. As you can see, it does look kind of ugly, but we can actually simplify this a little bit more. This is really when you square that, that becomes a 4, and 4 times the previous number in the front the number in the front, that becomes an 8. So you can do an 8 pi. Maybe this is a little bit cleaner if you like it that way. If you don't, that's okay too. Whichever makes you happier. You guys are doing an amazing job here. Okay, fine. So we wrote down the formula for the volume. We go ahead and we integrate math 9 from 0 to 1. Type that in. 1 over 8. Oh, don't forget the pi. Okay, 1 minus x. Now, by the way, the letter y is there, but we're using x because the calculator doesn't have the letter y. X and y are just variables, so just because I'm using y there doesn't mean I can't use x there, right? Because they're just variables. Dx, enter, gives me a volume of 0.982. Okay, so 0.098, that should be enough. Okay. Good job. We'll skip the last part, and I'll see you in class.